All right, so let's talk a little bit about entropy. I don't want to get too deep into the woods in entropy because, or deep into the weeds, because there's a lot going on for entropy. Entropy, like the simple definition that always gets bandied about, is that entropy is how disordered a system is. So what does that mean? That means like, is something organized or is it really disorganized? That's like a simple definition of entropy. If you've cleaned your room up, low entropy. If it's at the end of the week and your room is sort of a disaster and there are clothes and papers and stuff everywhere, then that's a high entropy state, and so that's disorder. Entropy is really a lot more complicated than that. What entropy really has to do with is probability or likelihood of a scenario happening. So one of the classic examples would be something really easy like, let's say that we drew a container that was connected and we had a bunch of molecules in it. So we've got two containers here. There's nothing there. The molecules can move freely between them. And so let's say that we've got like 20 molecules in there. Okay? So could 20 molecules be on one side and none on the other side? Assuming we're talking about gas molecules that can flow freely. Well, yeah, absolutely. That could happen, but it's pretty darn unlikely. Okay? Whereas a much more likely scenario is that there are some molecules over here and some over here, probably somewhere around 10 and 10, right? That's probably the most likely scenario. Maybe 9 and 11, there's a certain probability of that happening. We could calculate all of that statistically. And so what entropy really boils down to is essentially probabilities, okay? What scenario has the greater number of probabilities or greater number of, quite often we'll talk about it in terms of positional probabilities. There are different places that molecules could be. If there's only one specific place that they could be, then that is a low entropy situation. Okay, so in terms of like a chemical reaction, if we had two things bonded together, two atoms bonded together, so they're this state, they're bonded together, low entropy, one particle now. Okay, they're together, they're one particle. If during the course of the reaction they break apart into two particles, that is now a higher entropy state. We would say their delta S in that case is positive because they have broken apart. That's a higher entropy state. Okay? So what if we had a more complicated molecule and it didn't like break apart, it wasn't as obvious? Well, in this case, these molecules or these atoms are all pretty well locked into place. They're in a ring, and so while there's a little bit of flex in the ring, where the atoms can actually go in relationship to each other is not very great. The positional probability is pretty low, therefore their entropy is probably pretty low. And then we go over to this side here and we've broken this bond, okay? And so they're spread apart. And of course we got single bonds now, right? And so single bonds, we can rotate around those single bonds in all kinds of different ways. And so there's a lot more positions that this molecule can be in. Therefore, this is a more entropic state than this one is. This one's locked into place. Things can move around a little bit more here. Traditionally, how does this work for us in an actual chemistry problem? It really, a lot of the times at least, it's going to work for us in this scenario where you've got a certain number of molecules that you're starting with, and then you've got a different number of molecules there at the end. Okay, so if you have more than you had at the beginning, then chances are you've probably increased entropy. Now, is that always the case? No, not necessarily. I mean, there are some exceptions to that. But in general, that's how we're going to look at our simple reactions that we're going to do and figure out, did the entropy go up or down? Again, consider the constraint of the molecules. Did you go from a certain number of, did you go from single bonds to double bonds? Are you able to flex around? Did you form a ring, which is going to be very constrained and very low entropy? All of those sorts of things come into play. Now, you'll see that we did entropy as delta S, and delta S is up here in our equation. Capital T is temperature in Kelvin. The reason for that is our units for entropy are usually in joules or kilojoules per Kelvin. Okay? And then we're going to plug that in here, multiply it by the temperature, and then we're going to get joules or kilojoules along with that same unit that we had for enthalpy before, and we're going to put those together to get Gibbs Free Energy. Okay, so let's talk about Gibbs Free Energy then, finally. So we're going to get back to the math part here in just a second, because that obviously is what we're worried about, plugging stuff in, or at least sort of figuring stuff out in terms of the signage so that we can plug it in here. Why is it called free energy? Okay, what does free energy mean? So the Gibbs Free Energy thing essentially boils down to that it is energy that is free to do work, okay? In the case of chemistry, why that really matters is that it's energy that would be free then to do work on things, okay? Energy that's going to be free for other reactions to happen. Again, I mentioned earlier in a lot of biochemical processes, you might have something that has a really highly negative delta G, and we'll talk about the negative positive here in a minute. In other words, there's a lot of free energy given off by one reaction that the next 5 reactions in the cycle might need, because they might need energy, okay? So Gibbs free energy is energy that's going to be given off that is freely available to be used for other reactions. Okay, and I put another equation up here, a really short one. I don't want you to get like too bogged down by this or anything, but the formula for this is that delta G is equal to the negative of the maximum work. And you're like, that's really weird. Why is it equal to the negative of the maximum work? Well, that leads us back to the equation and what really matters here in terms of signage. Okay, so what matters in terms of signage is that a negative delta G means that a process is spontaneous. Okay, or we would also use in the terminology that's really sort of currently a little bit more in favor is that we would call the process thermodynamically favorable. Okay, I should have put in here process. Okay, process, reaction, whatever we're doing. That process is spontaneous if the delta G is negative. Okay, if delta G is positive, then that means the process is non-spontaneous. And how does that work? Well, if I have a positive delta G, then I can do a negative amount of work. Okay? In other words, I'm not doing work. In fact, I need more energy to make work happen in that case. That my project is pulling energy in. If delta G is negative though, okay, if there's a negative here, then that becomes a positive, and so we can then do work. So delta G being negative means that the process is spontaneous, that it's going to go forward the way that we wrote it up, that our reaction is going to go forward in the way that we intended it to go. So what does that mean for us up here in terms of our delightful reaction? And real quick, let me just throw down 2 new terms for you that I don't think are going to be difficult for you because we've already done enthalpy. So we've got exergonic and endergonic processes then. Exergonic processes are processes that release energy, okay? In other words, they are spontaneous. They have a negative delta G. Energy is free then and available to the surroundings for work to be done. And so endergonic means that it is a non-spontaneous process. And real quick, I'll just go ahead and put there again so that if you're just taking notes there, that you can see what you got. Positive delta G means that something is endergonic. Negative delta G means that it is exergonic and spontaneous, and it's going to happen and energy is being released into the system. So we have essentially 2 parts of our equation here that matter. We have enthalpy and entropy, okay? And so what that means for us is that we can have a positive or a negative sign for delta H. We can have a positive or a negative sign for entropy. We, of course, can't have a negative sign for temperature because we only do temperature in kelvins, right? For that very reason that we don't have any negatives. Okay, so we can plug things in then, and once we plug everything in, and we could, if we had numbers, we could plug the numbers in and see then what do we come out with here in terms of delta G. Well, what you can kind of see here is that, so what happens if I have, let's just say, let's walk through a couple scenarios real quick. Let's say that I've got a positive delta H, meaning that it needs heat going into it, okay? So it is endothermic, pulling energy into itself. Okay, but then let's say that also it's really entropic, that I have a high, that I've got a positive entropy. In other words, I'm putting energy in and it's getting more disordered. So what does that say then? Well, what does it say then? Well, I've got a negative sign here, right? It's minus T delta S. So that makes this whole part of the equation, okay, the entropy term or the entropy part of the equation, that makes this whole part negative and this whole part positive. Okay, so you've got 2 parts there. So if this part is bigger, then it's spontaneous. But if this part, if my enthalpy part is bigger, then it's non-spontaneous, then it's endergonic. Okay, so you can see there that if we have a reaction that we know the entropy of and we know the enthalpy of, that we can do some sort of controls of it by controlling the temperature. If I had a really high temperature here, then that makes this, the number for this part of the equation, okay, that makes this a much bigger negative, and it can probably, the term we would use is it dominates the enthalpy. So the entropy would dominate the enthalpy, and therefore we would get a negative delta G. Negative delta G is exergonic. That is spontaneous. That means that the reaction is going to happen. And of course, we can tie all of that back into equilibrium and all that stuff that we're not going to do in this particular video. So what about, let's do another scenario. Well, what if we have a case where we've got a negative enthalpy, okay? And that's favorable because remember, we're trying to get the negative delta G. So having negatives is good in terms of enthalpy. So if I've got a negative enthalpy, then what happens if my system, the entropy goes down? In other words, let's say that maybe it was 2 molecules and now it's 1 molecule. Okay, well that means that the entropy has decreased, which you're like, okay, great, that's negative. But it's not really, because remember the negative here in the middle, and those two negatives together for this part of the equation make it a positive. Okay? And so then again, what matters is how big is my temperature. If my temperature is really low, okay, so at low temperatures, then the numerical value of the positive part of the equation here is pretty small. And it will therefore be dominated or overwhelmed by the enthalpy part of the equation, which will mean negative delta G. Okay? So those are sort of the opposite scenarios. What if, so let's say, those are two of the essentially 4 possibilities that we can have with this equation. So what if then I said, well, let's say that I've got a exothermic reaction. In other words, I got to put heat in. Well, that's not good. Positive sign there. All right. But maybe we can make up for it on the other part of the equation. But then let's say that my entropy is going down and my system is becoming more ordered. I had to put energy in and it's getting more ordered. Okay. Less entropy. Well, we put this negative down here. Remember that that negative comes down. That makes this all a positive. Now I've got 2 positives. And so what that means is if the enthalpy is endothermic and the system is becoming more ordered, there is no way for that reaction to become spontaneous. Okay, there's nothing spontaneous about that. That reaction isn't going to happen unless something in the scenario here changes to cause it to happen. Okay, what about the 4th possibility here? Well, for my 4th possibility, what if my reaction was exothermic, it's releasing energy, negative sign here, that's a plus, okay, we're in good shape there. And then what if my entropy was increasing? Okay, in other words, it was going up. Well, if I am then subtracting that, right, because there's my subtraction sign, then that becomes a negative, and so then I've got 2 negatives going together, which is good, because 2 negatives mean that if it's becoming more disordered and it's exothermic, it means that that thing is spontaneous every time. It is always exergonic. Okay? So those are your 4 possibilities there. Remember, like at its heart, what you're looking for is you're looking at this, comparing signs and numbers if you have them. That sort of depends on the class you're doing. If you're doing something really quantitative and you're plugging in the numbers, you can see that. And you can read all this stuff off the table, and we'll do some calculations like that. But a lot of scenarios and concepts, you don't really have that. You're sort of saying, okay, it becomes more disordered and I know that it's exothermic for this reason. Okay, so under what situations then do I get a negative delta G that will make this spontaneous? Okay, and so that's when you start to consider the temperatures. Is it low temperature? Okay, because at a low temperature, then this part of the equation is really small and the enthalpy dominates. Is it high temperature, in which this part of the equation is really big and the entropy part of the equation really dominates? So just keep that in mind as we're walking through, and we'll try to work some more of those problems in class. But that's a real quick review of Gibbs Free Energy for those of you that might have needed a little bit more of a boost or a reminder for you. All right? Thanks, kiddos.